And now we start. And I want to invite the first chairman of the first session, the two keynotes, Professor Udi Gazit, Ehud Gazit, I should say, that really take a very big role in the establishment of this institute from the first days as the vice president for R&D of Tel Aviv University, and then as the chief scientist of the Ministry of Science and Technology that supported and talked to the R&D and was actually their role. And then ongoing as our head of the steering committee and all, the really hard minutes that I had, he was my support, and he was the one who helped me to go on and to make it really happen. So, and just yesterday, he got the Rappaport Prize. So, Mazal Tov. So, he's a very renowned scientist, and more than that, a very special person. Udi, please.
Thank you, Mira. It's really a pleasure to be here. I wouldn't be here if it wasn't Mira. Who convinced, as was said, Mira is one of a kind, and I think that much of the activity here is related to Mira. We are now starting with the scientific session. And I think that not only we are in a very special place, but we have very unique scientific program. Both President Klafter and Mayor Litvinov mentioned the remoteness of this area. I feel a little bit like a Gordon conference. Those of you in the science, it's you have high quality science. You need to be in one place because you cannot go to any other. It's the ideology, and we're thinking of offering this as a site for Gordon conferences. We will start with Professor Colin Price. Colin is from the Porter School at Tel Aviv University. Is a world expert in atmospheric research, studying lightning and thunderstorms, less related to this area. Recently, he moved closer to biology, studying the electromagnetic waves of Earth and their effect on the biological system. But today he will speak about the Dead Sea, from past to the future. Colin, please. Okay. Ken, Mish, we can turn the lights down. Okay, so good morning to everyone. My name is Colin Price. I'm the head of the Department of Environmental Studies at the Porter School of the Environment and Earth Sciences. Mira asked me to give a talk about the history of this region and what makes it so unique. So I'm actually stepping a little bit out of my comfort zone. And although I have an undergraduate degree in geophysics, this is the first time I'm actually talking about the geophysical history of this region. And so there are a few people in this room who know a lot more than me, but we'll see how it goes. So this is a picture from space of our region. To put us in context, we can see the Nile Delta, Egypt. This green region is the Nile River, where most of the people in Egypt live, the green vegetation. You can see the Mediterranean Sea, Cyprus, the Sinai Peninsula, the Red Sea, the Suez Canal, and over here we have, in the red circle, where we're located here today at the Dead Sea. With Jordan on the east side, Israel, you can even see the border between Israel and Egypt, which you can actually see the different vegetation here along the border. So I changed the title a little bit to give you a geophysical history of this region, of how we actually got to this location, and the special, unique location and how it was created. So, if we need to tell the story about the Dead Sea, we have to go back maybe 250 million years. 250 million years, all the continents were actually clumped together in one large continent, which we call Pangaea. You can see the outlines of the continents today: Africa, South America, North America. If anyone's ever taken a look at the map of the world, you can see that Africa and South America can fit together like pieces of a jigsaw puzzle. And so 250 million years ago, all the continents were together in one large continent with one very large ocean. And since the 1960s, we know about plate tectonics and continental drift. And so from about 250 million years ago, things have started to move around. Well, they've been moving all the time. The Earth's a very dynamic planet. Underneath us, under the crust, we have the mantle with convection, the lava which comes out in volcanoes. Things are moving continuously. And you can think of the Earth as made up of pieces of a puzzle, that the continents are moving continuously. And you can see the clock at the bottom in millions of years before the present. In fact, if we can see that start again from 250 million years ago, approximately 100 million years ago, where we are today actually had a sea which connected the Mediterranean, the Indian Ocean. We had this ocean between the Atlantic, the Mediterranean, the Indian Ocean were all connected, and we were not actually connected to Asia and to Europe. India, you see here, India went crashing into Asia, which resulted in the building of the Himalayas and Mount Everest. So this continues moving today. This is a very dynamic planet. It never stops. And if we look at the situation today, the different colored pieces here are actually the different pieces of the puzzle. Today, where we're sitting today, we're located here close to the junction of the green, yellow, and orange plates. It's called a triple junction, actually. We're close to it. The Arabian plate, the orange one, the Arabian plate is the yellow one, the African plate, and the Eurasian plate. And these are continuously moving on top of the mantle of the Earth. If we zoom into this, we can see our part of the globe here, where the Dead Sea, where we're sitting here, we're sitting right on the edge of two of these plates, the Arabian plate and the African plate. And where we're sitting here, the motion of these plates is actually horizontal. We've got a fault zone. Dov mentioned that we're at a break, but with no city. But this is a physical break as well, that the crust is moving. And the opposite side of the Dead Sea, the Jordan on the other side, is actually moving north relative to us at about 6 millimeters every year. And this we know from GPS satellites and antenna on the ground. The implication in that about 50 million years, Saudi Arabia will be opposite us on the other side of the Dead Sea and not Jordan. We can see the different types of plate boundaries in the Red Sea. This red line, we're actually having a spreading of the ocean. And so the Red Sea is actually opening up. And the Arabian plate is actually being separated from Africa over long periods of time. And these triangles here is where the plates are actually colliding with each other and resulting in mountain building or volcanoes, for example, Mount Etna here in Italy. And so these areas are where in India and the Himalayas, where we're having collisions of the plates coming together. But in our region, we have the sliding motion, this transform fault, where the Jordan is actually moving north relative to Israel. And this results in many earthquakes. It's a very dynamic area. We have wherever we have this motion, whether it's a collisional motion or a side lateral motion, this is where pressure builds up between the pieces of the puzzle, and when the pressure is released, we have earthquakes. So these show you, these little circles are all the earthquakes in this region in the last 100 years or so. And the Dead Sea region is a very seismically active region. We'll hear more about this talks later this afternoon about the earthquakes in this region. And we know this also from history. The last big earthquake was in 1927, not too far from here in Jericho. Caused lots of damage in Jerusalem, in Tzfat, in many places around Israel. And so from our knowledge, we know that in the past we've had big earthquakes, and the implications that we'll have big earthquakes also in the future. The question is when? 8 years? We'll remember that. That's being recorded. We'll check with that. So how did the Dead Sea form in this region? So we have this fault region that the plates are rubbing together. Well, it turns out there's certain features which can form when we have these two plates. Israel is going south relative to Jordan. Jordan's going north. And sometimes parts of the continent blocks get pulled apart in what we call pull-apart basins. So this part north is going north and south. And these blocks of land can actually just sink and form a basin and form lakes like the Dead Sea. We can also have this tension which can actually be sideways even though that the blocks are moving north and south relative to each other. And so all the way along the Dead Sea fault line, we can see this has been happening over history from the south in the Red Sea to the Dead Sea. The Sea of Galilee is another one of these pull-apart basins where the land is actually sunk and formed a basin. And we can go up into Syria until we get into Turkey. All along the fault line, we have these basins which have been formed and formed the Dead Sea and the Sea of Galilee to the north. And if we take a slice through this region from the Med to the Dead, the Med Sea to the Dead Sea, because of these basins which have been formed, some of them have actually sunk below sea level. So if we take a slice across here, we can see that in the Dead Sea, the level of the Dead Sea is now about 430 meters below the sea level in the Mediterranean. And this is due to this horizontal motion, which has resulted in this pull-apart basins being formed, and both the Dead Sea and the Sea of Galilee are both below sea level because of the formation of these basins. So this tells us why we have these areas below sea level, but why is the Dead Sea so salty? We can have these basins without the extreme salinity. Well, it turns out we saw the motion of the continents in the beginning, continental drift and the plate tectonics. Well, it turns out that up to about 100,000 years ago, the Dead Sea and the whole of the valley here were actually connected to the Mediterranean Sea through the Jezreel Valley. And water from the Mediterranean actually came in and filled up this whole region into a lake we called Lake Lisan. But around about 100,000 years ago, we had uplift in the northern part of Israel, which kind of blocked off this connection to the Mediterranean Sea, leaving us with this long lake from the Sea of Galilee in the north to south of the Dead Sea. All of this valley was filled up with water in Lake Lisan. Today, the salinity in the Dead Sea is around about 35%, 10 times more than the salinity of the Mediterranean Sea. The oceans are normally 3.5% salinity, so we have 10 times more salt and salinity in the Dead Sea. We can see here the types of minerals and the amounts in the Dead Sea relative to the Mediterranean or to the other ocean water. So chloride, we have 10 times more chloride in the Dead Sea water than from regular seawater. Magnesium, maybe 40 times more magnesium. Sodium, also 3 to 4 times more. Calcium, huge amounts of calcium, potassium, bromide. And we heard that this is actually used by the industries not far from here to remove these minerals and use them to sell them to the rest of the world. As a result of all this salt in the water, the Dead Sea water is actually very dense relative to us or to fresh water. So the Dead Sea is about 1.24 kilograms per liter of water, compared with fresh water and our bodies, which is less than 1 kilogram per liter, and therefore we float in the Dead Sea. We float because we're much lighter than the Dead Sea water, which is dense because of all the salt we have in the water. But that doesn't explain yet why so salty. So if we want to try to explain why so salty, we need to look at the rainfall gradient we have from north to south. On the right, we can see the rainfall distribution showing in the northern part of Israel, we have close to 1,000 millimeters of rainfall every year. Compared with the Dead Sea, which is less than 100. In fact, it's less than 50 millimeters per year here at the Dead Sea. So in the northern part, where we have the Sea of Galilee, we have lots of rainfall. It's also cooler there, so we'll have less evaporation. And so overall, we have more sweet water going in, and this lake existed for tens of thousands of years, producing the more sweet water in the north. But in the south, we have very little water flowing in. We have lots of evaporation because of the temperature. And so over tens of thousands of years, we've had lots of evaporation and becoming more and more salty, the water. And eventually, when it becomes saturated, we have deposition of salt layers, what we call evaporites. So evaporites are basically salt layers which are precipitated out of over the lake because of enhanced evaporation. Once we get saturation, we can actually have the deposition of salt layers. And we know that when we look at geophysical sections through this region, from the west in Israel to the east in Jordan, first of all, we can see these fractures where the basin has actually fallen. So the sediments have, this is where the basin has actually formed in the Dead Sea. But this darker region is the salt evaporites which were formed in the, I think this is the Pliocene geological period, these salt layers, evaporite layers. And it turns out that salt has a lower density than the surrounding sediments, and so that it actually forces its way up through the sediments, making it even to the surface, similar to what we have in a lava lamp, where we have the low density lava, the warmer lava going up. Similar with the salt forms what we call a diaper, and it moves up and can actually make it to the surface, which gives us the salt to increase the salinity in the Dead Sea. And this you can see close to the surface near the Mount Sdom, where you have caves which are inside the solid salt. If you drive near the Dead Sea hotels, you can actually see the solid salt on the side of the road, which has come up from the sediments which were buried over many generations. So this is the reason it's so salty, because of the climate, which is a lot of evaporation, and the production of these evaporites over time, which are basically solid salt. If we look at the watershed around the Dead Sea, so this outline shows you the watershed where all the rainfall forming inside the solid curve flows into the Dead Sea. The Dead Sea, again, is the lowest point, so nothing leaves the Dead Sea. But from even up in the Golan Heights down to the south of Israel near Eilat, we have streams which will bring the water towards the Dead Sea. We can also see the outline of the old lake Lisan. And as we heard from Dov, because of this, we suffer here, even last week, from a lot of flash floods in this region. Even though there's not much rainfall, when it does fall, the ground is very clayey, doesn't allow the water to fall in. We have very steep terrain here, and so we have many flash floods, which is closer to my area of research. Even last week, and for those living in Israel, we know that even last year in April, there were 10 teenagers who were killed in a flash flood not too far from here, where the water levels can rise extremely quickly from just a small amount of rainfall, which gets funneled into these valleys and flowing towards the Dead Sea. Well, if we're talking about water, we also have to talk a little bit about the history of Israel related to water, which is related to the Dead Sea. And this is in the 1960s. Israel built a national water carrier to bring water from the Sea of Galilee to the population living in the center and the south of the country, also for irrigation. And this huge project built tunnels and canals and pumps to bring the fresh water to where people are living. But at the same time, it diverted water from the Jordan River and from the Dead Sea. And so from the 1960s, we started to see less water flowing in to the Dead Sea. And now when we look from satellite images, we can see from 1972, 1989, and 2011, dramatic decrease, a lowering of the level of the Dead Sea. Approximately 1 meter every year, the Dead Sea is going down because we have very little water coming in and a lot leaving due to evaporation. And as we heard, this is resulting in new natural hazards, sinkholes. this region of the Dead Sea, which was covered with water maybe a decade or two ago, once the water disappears, we have salt underneath, which gets dissolved by the fresh water from rainwater and floods. And this develops cavities under the ground, which eventually collapse. And so these sinkholes are becoming a big hazard in the region of the Dead Sea. Also for infrastructure, roads are collapsing, beaches have to be closed, and I don't think we really have a solution for this at the moment. The weather, we heard about the extreme conditions for the weather. In the summer months, we can see the average temperature is around about 39 degrees. In June, July, August, this is about 102, 103 Fahrenheit for our visitors from the States. But extreme temperatures up to 47 degrees. Rainfall, no rainfall in the summer, and if we look generally throughout the year, we have about 41, 42 millimeters per year, and again, not too far to the north, we have up to 1,000 millimeters per year. So a very strong gradient in rainfall, very dry conditions, very hot conditions, and the humidity as well is always below 50% relative humidity. So very extreme weather conditions, but there are some benefits. Being 400 meters below sea level, we actually have higher atmospheric pressure. Higher atmospheric pressure means we actually have more oxygen in the air per liter of air. About 6 to 8% more oxygen. The pressure, the atmospheric pressure here is around about 1,060 millibars or hectopascal. In Tel Aviv, it's about 1,000. So we have an extra amount of air here, which gives us more concentration of oxygen. The opposite occurs when we go up a mountain. At the top of a mountain, we don't have enough oxygen. But when we come down to the Dead Sea, we have extra oxygen. Helps us. Also, the UV, the ultraviolet radiation, particularly UVB, is also less at the Dead Sea because we have less atmosphere. We have more atmosphere to go through. This varies as a function of wavelength, but these factors actually have great health benefits, and I think we'll hear later on about the health benefits in this region. Finally, the geophysical history has also influenced human history. This part of the world has actually been where we have Homo sapiens have actually left Africa and gone to the rest of the world about 150, 200,000 years ago, spreading into Asia, Europe, North America, even to Southeast Asia. And so this has actually got a huge amount of human history, which obviously we know about. Masada is right here. The Dead Sea Scroll, biblical studies. Obviously, these are fairly modern compared with Homo sapiens leaving Africa. But this is the geophysical history of the combination of the continents also influenced the human history of this region. And finally, I wonder if anyone can recognize this image. Who? Very good. I don't know who said that, but this is actually a picture from Mars. And you've been there? Maybe you took the picture. The reason I show this is because as we sit here now, there's a project not far from here called DMARS, where there are students and researchers who are trying to simulate life on Mars in this environment, in this extreme environment. And we're now looking at using this environment around us here to try to understand the conditions maybe on Mars in the future. And so we started the lecture looking from space at this region, and I'll end it with saying that maybe this region will also give us insights for life on Mars in the future. So I'd just like to summarize that we have a very unique history for this region of the Dead Sea, very promising future, and the promising future will be explained by Mira in the lecture to follow. So thank you very much.